Hi everybody. This next section 6.2 is going to be about the binomial probability distribution, and so these will be the objectives for this section. So we'll look at determine whether a probability experiment is a binomial distribution or not, compute probabilities of a binomial experiment, compute the mean and standard deviation of a binomial random variable, and construct binomial probability histograms. So let's look at objective 1, determine whether a probability experiment is a binomial experiment, right? So what does it mean to be a binomial experiment? So to be a binomial experiment, it has to satisfy the following 4 criteria. The experiment is performed a fixed number of times, so that means you don't do it until something happens. You do it, you say, okay, I'm going to do this experiment 100 times or 50 times, and that's how many times you don't do it, right? It's not like you flip a coin until you get heads and then you stop. The trials are independent. This means that the outcomes of the trials will not affect the outcomes of the other trials. So again, this is like flipping a coin. It's sort of the basic example of a binomial experiment, because you either get heads or tails, right? And flipping a coin once, shouldn't affect the next time whether it comes up heads or tails. For each trial, there are 2 mutually exclusive outcomes. So like I said, heads or tails, you can think of flipping a coin for this. And then 4, the probability of success is fixed for each trial of the experiment, right? So again, this would also be like flipping a coin. So for each time you flip a coin, you have a 50% chance of getting heads or tails. It's not like one time you have a 75% chance of getting heads, and then the next time you have a 25% chance of getting tails, and then the next time you have a 13% chance of getting heads, and then a 93% chance of getting tails, right? So when you think of a binomial probability experiment, the prototypical example, the thing you want to sort of keep in mind is the idea of flipping a coin, right? So you say, I'm going to flip a coin like 10 times. Again, the trials are independent. For each trial, there's heads or tails, 2 mutually exclusive outcomes, and then the probability is always the same, 50% heads and 50% tails. Sometimes also called a Bernoulli trial, by the way, instead of a binomial trial. But so as far as notation used in binomial probability experiments, there are n independent trials. So n is the number of trials. P is the probability of what will determine to be a success, and 1 or 100% minus p is the probability of the failure. Capital X be the binomial random variable that denotes the number of successes in the n independent trials of the experiment. So X again is the number of successes. So if you're measuring success as like coming up heads, X would be the number of times you've come up heads. So let's look at some examples here. Player rolls a pair of fair dice 10 times. The number X in this case represents the number of successes is the number of 7s rolled and recorded, right? This would be a binomial experiment. And then here's another example. So the question is this or is this not a binomial experiment? So the 11 largest airlines had a one-time percentage of 84.7% in November, according to the Air Travel Consumer Reports. That means that the planes were on time 84.7% of the time. And in order to assess reasons for a delay, an official with the FAA randomly selects flights until she finds 10 that were not on time. The number of X flights that need to be selected is recorded. So the question is this a binomial experiment or not? No, because in this case, the person searches for 10 until she finds 10. So you don't have a fixed number of trials, right? You'd have to say, okay, I'm going to measure the first 100 aircraft, and that's it, right? You don't cull through the data until you find what you're looking for. Let's look at another example. So in a class of 30 students, 55% are female. The instructor randomly selects for students. The number of X females selected is recorded. Right? And this is not a binomial experiment because the trials are not independent, right? So if a person selects a female student, then the probability that they'll select another female student goes down, right? So the probabilities will also change, right? Okay, so hopefully that'll help you understand what a binomial experiment is and what it is not. So let's look at objective 2 and how to actually compute binomial probabilities now that we know what they are. So let's look at an example. Let's go back to this example with, well, I guess it's a slightly different example here. But we've got 11 largest air carriers had an on-time percentage of 79%. Suppose that 4 flights are randomly selected from May, and the number of on-time flights is recorded. Construct a probability distribution for random variable x using a tree diagram. So in order to compute the tree diagram, and you can see a picture of this tree diagram on page 336, there's sort of a quicker way to do this than using the tree diagram. You can just compute this using the formula on page 337. So the formula basically comes from the reasoning in the tree diagram, but this is the formula that you would use to compute the probability of obtaining x successes of n independent trials. So in this case, NCX is what we looked at in chapter 5. This is n combination x, or n choose x. P, remember, is the probability of success raised to the x power, so you're taking the number of successes, you're taking the probability of success raised to the number of successes, and then 1 minus p is the probability of failure raised to the number of failures. So let's look at an example, because this formula may not make complete sense here. Another thing too that you might see is at least or greater than. They might want you to find the probability instead of like 10 successes, they might want you to find the probability of, say, 5 or fewer successes or greater than. So just remember, this is what these symbols mean. And you can compute this in StatCrunch by going to calculators and going to binomial and entering the appropriate information as well. But let's just do an example of how to do this by hand. So let's say that in a random sample of 20 car-owning households, what is the probability exactly 5 have 3 or more cars? So 35% of all car-owning households have 3 or more cars. And in this case, you want to know exactly 5, so we're calculating P of 5. So in this case, you would plug in, you have total 20 cars, you're trying to find the probability of 5, and so you raise the 0.35 to the 5th power, take the 1 minus the 0.35 raised to this power. That will give you the probability that exactly 5 have 3 or more cars. So that means there's a 12.72% chance that exactly 5 out of the 20 households have 3 or more cars. Now you can do a similar problem where, let's say, you want to figure out what's the probability that less than 4 have 3 or more cars. So in this case, you would be looking for this. So another way of saying this is the probability of x is less than or equal to 3. So what you'd have to do is calculate the probability distribution for each one of those cases, the probability of having 0 cars, 1 car, 2 car, 3 cars, and then add that all together. You can also use table 4 in your book. The cumulative probability distribution is probably the easiest way to do this, or you can use table 3. So, and then I should mention, each one of these you'd have to calculate by using the formula again, right? So for the first one, you'd calculate, 20C0 of 0.35 to the 0 power times 1.35 to the 20th power. For P sub 1, you'd calculate 20C sub 1 of 0.35 to the 1st power times 1 minus 0.35 to the 19th power, etc. Let's look at another example. What is the probability that at least 4 have 3 or more cars? So another way of saying this is, since this is an at least problem, you can say what's the probability that you have 1 minus P of x is less than or equal to 3. So we could just take our answer from the previous problem here, 0.0444, and that would give you about a 95.56% chance. Okay, so that should show you at least roughly how to calculate probability distributions. I guess another way you could do this one too is you could calculate, P of 4 plus P of 5 plus P of 6 plus P of 7 all the way up to P of 20 and add those together. But it's a lot easier to just do it this way. Okay, so objective 3 is compute the mean and standard deviation of a binomial random variable. And so here's the formula for the mean and the standard deviation of a binomial distribution. So again, this would be the sort of the center and the spread. So let's look at an example here. So we want to determine the mean and standard deviation of the car-owning households that have 3 or more cars. So in this case, you just take 400, the sample size, times the probability of success, 0.35, which gives you 140. And then you'd have sigma sub x is equal to 9.54. So that would give you an example of how to do that. And then objective 4 is construct the binomial probability histogram. So as far as constructing histograms, this probably isn't something I'm going to have you guys do, but you can do this for various numbers here. I'll just give you show you what the graphs looks like for different values of p. And so you'll notice here as the shape becomes, as n becomes larger, the shape becomes more and more normal. So it becomes more bell-shaped. So just something to be aware of, not anything you're going to have to use here. And so keep in mind that, for large sample sizes you can use the empirical rule then if it's a normal distribution. Let's just look at one example here. And then I think that'll, yeah, let's just look at one example here, and then I think that should wrap up this section. So in this case, the mean would be 140. The standard deviation would be 9.54. So then, I guess 2 standard deviations away on one side, on the left and the right, would give you 120.9 and 159.1. And since this result should be unusual, right, because 162 is more than that number. Okay, well that should pretty much wrap up 6.2, so we're skipping 6.3 and 6.4, those sections are optional. And then we'll look at chapter 7 next, right? As usual, if you guys have questions, let me know.